Hello, my name is Noah Schwalb. Today I'm going to be going over my summer research with Dr. Kanistras in the RCU program. So first I'll start with a quick outline of the presentation. First we have our motivation for the work. Then we'll talk about our previous work done by colleagues in our field. Then we'll mention the methodology that we used to design and develop our algorithm. We'll talk about the results we get when we apply that methodology to a small-scale UAV. And we'll talk about some of the future work that we define for this project after it concludes, and we'll end on some of the references we used in this presentation. So our main motivation for this stems from two things: fluid structure interactions and aerodynamic optimization. These fluid structure interactions are essentially systems where we have a fluid and we have a structure. These structures can be aircraft, it can be a turbine, it can be whatever you want. In our case, it will be an aircraft, and the fluid in our case will be air. So we want to see if we can characterize this system of an aircraft and air using a mathematical model. This mathematical model we want to develop will help us predict the output of the system. So we can give it a different type of input, we can give it a different wing length, we can give it a different winglet length, we can give it all these different parameters, and we want to see how it's going to react when we do that. The other thing is the aerodynamic optimization. This will kind of help us find the best aircraft configuration for a specific set of mission requirements. So whether it be to find the maximum endurance of an aircraft or whether it be to find the maximum weight possible to carry, this all falls under optimization for aerodynamics. So some previous work done by others in the field, people use experimental and computational methods. Experimentally, what a lot of people do is they'll build physical prototypes and then they'll run each prototype in a one-to-one experiment. This is sometimes called one-at-a-time sensitivity analysis, and is very expensive to undertake. Computationally, a lot of people use a method called free-form deformation, which is where you build a computational model of the prototype, you analyze it using a fluid flow solver like Star CCM+, or ANSYS, or CFX, and many others out there. And then from that solution that you get from that software, you'll slightly change the geometry and then reanalyze it again, and you'll keep doing that process until you get a good solution. That good solution is defined by the user. So onto our methodology. First, we have the 3D winglet parameterization. This is the actual main geometry and the 3D component of the winglet itself. We reduced it down to 5 basic parameters: sweep, twist, cant, span, and thickness. They're all represented here in figure 2 in their respective places. Note here that span represents actually span percent of the wing, as noted in figure 2. This actually means that if the span is set to 0.05, it means that the winglet is 5% of the span of the actual wing itself, which means that if the entire wing, including the winglet, is 1 meter, that the winglet will be 0.05 meters, and the wing itself will be 0.95 meters. So that covers the 3D component of the parameterization, but for each 2D cross section, there's a different type of parameterization we use called the airfoil parameterization. That is what is a 2D section of a wing is called an airfoil. So what the method that we chose is called the improved geometric parameterization method, and this decouples the thickness and camber of an airfoil, which means we can kind of change them differently. We can see how each of them affect whatever output we want. So the thickness and camber parameters are listed in figure 3, and the camber represents mostly the curvature of the airfoil, and the thickness represents the actual width, like the girth of the airfoil. So combining these two methods of parameterization for the winglet, we have the actual winglet itself, but the algorithm we wrote will include all the necessary components, which is not just those two parameterization methods, but also the aerodynamic simulations and the curve fitting algorithm we chose. Figure 4 kind of shows the flow diagram of this whole algorithm, and these aerodynamic simulations will actually detail the flow solver of the fluid structure system. So this is essentially when we put that model into that software like ANSYS or Star CCM+, and there's plenty of others out there, and we get a data point out of it. And all these different data points represent each different model. So when we vary all these different models, we get all these different data points. We now put those into the curve fitting algorithm. This curve fitting algorithm will tell us, here's the curve, the coefficients of this curve that best represent this data set. Now it's limited to the type of function we input into it, but for these preliminary analysis and this methodology, it does its purpose. So the results, when we put it into a small scale UAV, when we vary 3 variables, which would be can't, span, and sweep, with the values listed up here, we get a function listed in figure 5. So this is a 4th order polynomial where x1 is the cant angle, x2 is span, and x3 is a sweep. And this resulting function here in figure 5 has an r-squared value of 0.7161. This value here is supposed to represent how well the actual function fits the data itself. So for future work, we can increase the fidelity of the model for the winglet parameterization. This can happen by adding more parameters itself. So we can make it a blended winglet. We can make it, we can add more taper, we can add taper ratio. We can add all these other different parameters to make it more detailed and more realistic to how people design aircraft right now. Along with that, we have the curve fitting, which we can improve on. This can be improved on by fitting a function to the design space that better matches the data set. Our r-squared value doesn't tell us, tells us that our polynomial doesn't fit the data set the best, but it gives us an idea of how the trends go. So if we find a function that better fits it, then we will have much better results in terms of curve fitting. But in the applications of this, we want to see if we can generate a much larger data set where we have 1,000 different span points, we have 1,000 different sweep points, 10,000 different cant angles, and see if we can get a much more detailed characterization of the design space. So here are the 2 references we used in this presentation, and this will conclude my presentation of our summer research. Thank you for your time.